Alrighty, welcome back to 454. Wow, that's echoey. Let's turn that off. All right, so just so we're on the even keel with the other course, I'll use Ashvin's slides that he provided me because there's a lot of diagrams. I want to make sure I cover everything since this is what you will need for, what is it, Lab 3 stuff. So this is dynamic memory. Most of it will probably be review. If I go too fast, stop me. If I need to go and explain anything, again, stop me. Basically, this is like talking about malloc. Everyone's used malloc before, and linked lists pretty much. So contents, yeah, so we'll do a bit of a background, alignment, memory management API, mostly malloc free. Some constraints, goals we have, fragmentation, everyone remembers that, hopefully. That is just wasted space. And then some basic dynamic allocation we can do. So lab 3, you're given a very basic memory allocator and you're supposed to make it better. And we'll go over some different techniques you might want to use, mostly using free lists, different versions of free lists, and then buddy allocation. You might have remembered we talked about buddy allocation a bit in 344, but again, we'll revisit it here, and then other things we might want to consider. So why do we want dynamic memory allocation? Well, might not know the size of the memory you need at compile time, right? Might get user input, might read from a file, something like that. And main memory apparently is precious, so you don't want to actually waste all of it, otherwise you'll be out of memory. Generally, not that big of a concern unless you are Chrome. So here is an aside. So this I've already showed before. We should know exactly what variables are on the stack, local variables, parameters, function arguments, return values, even though that one's not quite true and the other ones also aren't super true either. They're usually passed in registers to be very, very fast, but you can actually address them as if they were on the stack and then they'll allocate stack space for you only if they're needed. Then the heap, that's used for dynamic memory allocations, used for malloc, and well, first question we should answer, why can't we always use the stack to allocate memory? What would be bad with that? Yeah.
When you go out of scope, there's no way to recover it.
Yeah, when you go out of scope, all of it's gone, right? Nothing's going to live longer than a function. So if our lifetimes are all the same, if the lifetimes of all our variables just exist for a function, that's great. They'll get all deallocated at once. Things will be nice and fast. But we don't always know, we might not even necessarily know the lifetime of our memory usage. And if it outlasts a function, well, we have to dynamically allocate it. All right, why would we learn about this? Well, it has to do with performance too. So the performance of doing all of the mallocs can actually affect your program, where it allocates memory, how smart it is about doing it. So, you know, you could just say don't even use malloc, just manage memory yourself. But there's a lot of different malloc implementations. We'll go over some of them in a later lecture, but like Firefox, Chrome, won't use the standard C malloc. They'll use something like JE malloc that we'll get into later. Or, I mean, you could, of course, just grab a bunch of memory yourself. You could nmap. You could just ask the kernel for a lot of memory and do your own memory or handle your own memory allocations if you want. Challenging, interesting, right? Actually doing this is quite involved, and making it scalable, making it work well on multiple cores is interesting, which you will get into in lab 4. So we won't start threads now. Lab 3, again, just single threaded. You'll get a good understanding of what happens under the hood, and yeah, apparently This is supposed to be so you learn more about pointers. Everyone loves pointers, right? Everyone's favorite topic of all time. I know it's mine. So apparently this is to force you to learn more about pointers and have fun with them. So memory allocators, they just assume memory is like a set of blocks. A block can be some variable size, contiguous, at least in virtual memory. And you can provide these blocks to the application. You can actually allocate explicitly, as we know, with malloc and free. In C++, you use new and delete. They do the same thing. New eventually just calls malloc. The only difference is in C++, it can actually figure out the size of types for you, which is much, much nicer than just mallocing and using size of all the time. But under the hood, new just calls malloc eventually. Delete just calls free eventually. So you can also have implicit memory management that you allocate memory and you don't free it explicitly. You let something like a garbage collector figure it out. You can use it in Java, ML, OCaml, whatever languages that you probably won't use, or Lisp. But the thing about this is, even if you use a garbage collector in Java, people think you just get deallocations for free, which is not true. You can easily leak memory in Java if it's still reachable and you don't actually null a pointer. Your garbage collector probably will think you might use it in the future, and that's why Java applications typically leak memory like a damn sieve. Yeah.
Does something like shared pointers, do those count as implicit or explicit?
So shared pointers would be explicit. So it's just, it explicitly does the new and free, but it knows, it's a bit smarter about when to free. So it pretty much does reference counting for the pointer, and it's just a managed pointer, which should probably be in this course, but is currently not. But we'll go into some different memory allocation stuff. That's more of like managing the lifetimes. So we had this before, slightly different diagram. So the typical process memory layout looks like this. You know, the kernel allocates some virtual address space for its own use that you can't touch. You usually have the stack at the top. That is a set size, grows down. You usually have some memory map region that, you know, that's where all the dynamic libraries get loaded to. Whenever you mmap, something like that, it'll generally pick a virtual address somewhere between the heap and the stack. And then the heap might be here. That is just one big region of memory. And things like malloc are actually supposed to use just the heap for the allocations, although most general allocators nowadays also do memory mapping, just to get bigger blocks of memory and hopefully free it a bit easier than just one giant region of memory that's all kind of contiguous. But for lab 3, you're just dealing with the heap. You don't get to memory map anything or do anything like that. And then, like, this is your uninitialized global variables in this section, initialized global variables in the data section. This will all be zeroed. And then the program text, that's just where your instructions live on memory. That will just be loaded for you whenever your program starts executing. All right, alignment. Who knows all the C++ or C alignment rules? Probably no one. So let's go over them quickly. So what is alignment? Basically, things start at a multiple of some address. So it'll start at, the address just needs to be divisible by some number k. So if things are 8-byte aligned, it means the address is either 0, 8, 16, It is always divisible by that address, aka all of those bits are just 0. So if I have some object of size k, where it's a multiple of word size, so word size is typically just the size of a pointer on this machine, on your machine. These slides are slightly old because 32-bit systems. Have any of you even used a 32-bit system? 1, 2. Yeah, so they were, I used them as a kid. That doesn't age me at all. But yeah, so back then, 32 bits. Word was 4 bytes, 32 bits. There's 8 bits to a byte. And malloc would always return things aligned to 8-byte boundaries, so double word size. And 64-bit systems, well, 8 bytes. So malloc actually returned double words, so everything is 16-byte aligned. So we can even see a demo of that because that is also not true today. So here is just a little example. I just malloc space for 10 integers. You would assume that, hey, well, if I'm mallocing space for 10 integers, they could all just be in a row, right? Every 4 bytes away from each other. So in here, I print off, aside from the first allocation, how far away or how many bytes in memory it is away from the previous allocation. So we can go ahead and run this to see what the alignment is. So if I run this, so the first allocation, really far away from the first chunk of memory I got. It's like 1,072 bytes. And then all the other ones are 32 bytes away. So anyone guess why I'm storing, I'm storing just 4 bytes. I'm asking for 4 bytes, but all the addresses I get are 32 bytes away from each other. Yeah?
Is it just a heuristic for assuming if you call something like realloc?
A heuristic, so if I have space for realloc, not quite. That's a good guess, though. Yeah?
Minimum size of allocation?
Minimum size of allocation? Why would there be a minimum size?
Blocks.
Blocks?
It's like nano or maybe even arena that's using to allocate these integers really quickly.
Not quite. Getting warmer, though. Any other guesses? Yeah?
Is it like better alignment for the cache maybe?
Better alignment for the cache? Somewhat, yeah.
Is it malloc's own internal tracking?
Malloc's own internal tracking, that is also part of the reason. So yeah, malloc might have some bookkeeping information associated with the entries it stuffs in there. So that could very well be one thing. The major thing is that malloc has no idea what I'm actually going to use the memory for. So if I have ints, they should be 4-byte aligned. If I have doubles or something like that are 8 bytes, those need to be 8-byte aligned. And turns out the largest data type on your system is just 32 bytes. So it has to assume the worst case, and everything has to be 32-byte aligned that gives back to you, because malloc has no idea what you're going to use that address for. So that's one of the reasons. And back in the day, this was 16 bytes away because we didn't have those giant instructions that tried to do a lot of things in parallel. But AVX actually requires 32 bytes aligned, so it's the largest alignment that your CPU actually needs. If I ran this directly on my Mac, their 16-byte aligned is the lowest I got, not 32. But if you run this on any x86 machine nowadays, you'll get 32. If you run it on the UG machines, it'll be 32. Yeah?
Why is it 16 for Mac?
It doesn't have the same instructions, so completely different instruction set. We only use the 32-byte values to load like special AVX instructions, which Mac CPUs don't have. They're a different architecture.
Right, but they have the ARM Neon ones, though.
Yeah, but they have different alignment requirements.
Oh, okay.
Yeah, so it's just
Yeah,
the alignment requirements of the CPU are slightly different. Yeah.
So what's with the really big jump at the beginning?
Yeah, so the really big jump at the beginning, it's just whatever they decided to do. So depends on the malloc implementation. I think this is just the standard C one. it probably has a space allocated for very, very short allocations, especially, and just jumped over some general space. So you can kind of see how it works. If I run it directly on my Mac, it jumps backwards and forwards a bit and shifts a little bit, but it kind of just depends on your system. Interesting to run this test and see what happens. But yeah, caches also had something to do with it. Well, that's just general alignment things. So yeah, why alignment? So if you don't have any alignment, data structures can start at any address, especially bad for caches, but CPUs as well. So if an integer just started at some weird address that was some odd address, and our cache block was 64 bytes, well, then how many cache blocks do we need for this integer? It could straddle the boundary, which I mentioned before when we started talking about caches. We want to make sure things fit on the cache, they're cache aligned. So if it's not even aligned to an even number of bytes, could easily be the case where you straddle the cache. So 1 byte is on one cache block, and the other 3 bytes are on another cache block. So that's really, really, really bad. So you should, again, like we reviewed before, try to fit everything on a cache as much as possible. So also, the cache accesses at like 64 bytes. CPUs generally like things aligned to the word size. When it's not aligned to the word size, just reading a simple data structure can take actually 2 reads on the CPU itself. Your caches will help with this, but if you have unaligned accesses, you'll notice most of the time your performance will be worse, even if it's on the same cache line. So 32-bit machines, don't have to worry about that, but they were 4-byte aligned, so the lower 2 bits had to be always 0. So to make sure that they're aligned to a word. So how do we align them? Well, luckily, our compilers do it for you. There are lots and lots of rules, especially with structs, that we'll go over to actually do most of the alignment for you. You can also suggest alignments to the compiler if you want to align to cache lines that it might not know about. And then libraries like malloc, they'll return aligned addresses for you. So if you want, one way to do that is if you have a struct that has 3 shorts, an array of 3 shorts in it, each short is 2 bytes. So this whole struct will be 6 bytes large. And if you want to make sure, and the whole alignment of the struct, it could start at any 2-byte boundary. So it would only be 2-byte aligned. If you want to make sure it's 8-byte aligned, then you could just do this attribute. It's like underscore underscore attribute. It's a built-in thing for Clang and GCC. And you could say, I want this struct aligned to the 8-byte boundary, so that if you declare one of these, it will always be aligned to 8 bytes. If you try and have 2 of them next to each other, there'll be a gap of 2 bytes. Yeah?
What size of stays 6?
Size of would be, I think size of would stay 6. I'm not 100% sure on that. I should check. But yeah, that's just if I allocate it. I think it might add padding to it, so I think size of might change to 8. I'd have to double check though. All right, so specific cases of alignment. Basically, they have to be aligned on the same byte boundary as the size of the type. So if I just have a char, doesn't have to be any special alignment, anything like that. It's aligned, it can go in any single byte. Otherwise, there'd be weird things if you had arrays of chars. If I have a short, which is 2 bytes, it's aligned at the 2-byte boundary, so the least significant bit is always 0. For types that are 4 bytes long, it's 4-byte aligned, so the last 2 bits are 0. 8-byte aligned, the last 3 bits are 0. And for the pointers, depends on the size. Nowadays, we're all 64-bit, so they'll all be 8 bytes, so they'll all be 8-byte aligned. So You can also, if you use a structure, within a structure, the offsets of the elements, so like where a field is in memory, actually will satisfy the element's alignment requirement itself. And for the overall structure, the rules are C will look through every single field, and then the total alignment of that structure will match the largest field in the structure. So the starting address would always match that. So we'll have a few examples. So if we have this struct S1, it has a char C that will have 1 byte, and then an array of 2 ints. So each int is 4 bytes. We got 2 of them. In total, the amount of memory we're using is 9 bytes, and the largest element is an int, which is 4. So how it will be laid out in memory is the rules of C are also that all of the fields will come in the order that you declared them in. So the first thing that will be stored in memory is this char C, and then the next 2 things will be, well, the next thing will be the array of integers. So in this entire structure, the largest thing is an int, so the entire structure needs to be aligned at a 4-byte boundary. So whatever pointer it starts at will be a multiple of 4. It'll be 4-byte aligned. Then the char doesn't have any alignment requirements. It will just start at the first byte. And then since the next field is the array, it has to start at a 4-byte boundary. So C will put in 3 bytes of padding here. So 3 bytes of padding that won't be used for anything, only used to make sure we have good alignment for the array. So the array would start off at a 4-byte alignment and then have 2 elements. So the total size of the structure is 12 bytes. Everyone all right with that? Fun. All right. So if we had something like this, so we just stuck a double at the end of it, well, now the double is the largest element. It is 8 bytes. So in total, right, our structure still has that 1-byte char, the array of 2 ints, and the 1 double. So we have like just raw 17 bytes in total. But we also have to make sure everything's aligned and laid out in memory in the same order. So our largest element is 8. So our pointer that goes to the structure will be 8-byte aligned. Like before, the char will start it off. It's the first thing. It would be at the beginning. We'd have 3 bytes of padding. Then we would have our 2 ints. Like before, it would end at byte 12. And now, well, we need to have an alignment of 8 for the double. So we need 4 bytes of padding to get us to the next multiple of 8. And then that's where our double would go at the very end. So in total, our structure would be 24 bytes. Yeah?
What's the purpose of the padding here if, like, we know every single value, I guess?
If we know every single value?
Like, we know every type, right? Like, before we had padding because we didn't know what the type might be.
We knew the types here, too.
No.
For...
That's fine, right?
Okay.
For the demo, right?
Yeah, the
32
demo.
bits for every type.
For malloc?
Like, before when we mallocked, we had to do the largest, like, type that we could store.
Yeah.
Padding.
Yeah.
But here, since we know every type in our struct, like, why do we still need the padding?
So we need the padding so that, like, the malloc, everything, it returns you a 32-bit align or 32-byte align pointer, right, which fits everything. Here, the alignment is the largest the alignment's the largest element here, right? So it does fit. So it will use the smallest one it can here, while malloc has to assume the worst case.
You still have to align them, right? Because the processor can, I know there's some processors that even refuse to read like 8-byte objects that aren't aligned by 8. Like they'll throw it in
Yeah, some will definitely do that.
Yeah, so you have to align these anyway, right? You just have to align them by the right amount.
Yeah, you just have to make sure they're aligned correctly. Yeah.
So our example before just illustrated that every block has to be aligned by the worst case data type, but like inside of each block, they just have to be aligned by the worst case in that struct.
Yeah, so this is just laying out the struct by itself, and malloc just gives you memory and it has no idea what you're going to do with it, right? But this is,
Boundary of each block has to be aligned to the worst case data type of the system.
yeah, malloc has to give you the worst case alignment. Otherwise, if it doesn't give you aligned things, things might just refuse to work depending on the instructions or whatever data you feed it. But this is just what memory I need for the struct by itself. So yeah, in this case, we needed 24 bytes in total, so we lost some to alignment. Yeah.
That means the most efficient use of memory using structs is if the programmer sorts
Yeah.
all the, what would you call them, like elements?
The fields, yeah.
Yeah, in increasing order.
Yeah, they don't necessarily have to be in increasing order, but
Otherwise, if I have like
you want to
a
reduce the
char
padding.
and a double, then like 5 more chars, then it'll be 1 byte, then you have 7 bytes empty, then a double,
Yeah.
1 char, char, char.
Yeah, so I mean, you could waste a lot of space if you did char double, char double, char double, char double, char double, right? So every time you do that, you're wasting 7 bytes worth of padding between every one. While if I was smart and I knew these rules, I could just do char, 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 double, 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 double. Sounds like I'm going to Tim Hortons or something. Yeah.
Sorry, I don't know if I missed something. Why doesn't like the compiler rearrange it for you?
Why doesn't the compiler arrange it for you? So that would make things a lot more complicated. So like calling conventions have to agree with each other, these have to agree with each other, right? The compiler has to agree with possibly other compilers. So there has to be a single set of rules for how to lay out a struct in memory that every single compiler agrees with. So they just made it very, very simple because back in the day, they assumed that you as a programmer will figure all this stuff out for you. Yeah, C++ follows the same rules. Classes are just structs, but they write a bit. They use pointers for you. But yeah, so how you declare fields actually matters. So I think that will come up next too. So yeah, also if you have arrays of structure, well, they're just arrays. So they'll just take the total size of the structure and lay it out. So if I have the structure S3 that has a short, int, and another short, well, within one of the structures, my largest thing is an int, so it will, my largest thing is an int, so the entire structure will be aligned to a 4-byte boundary. But since I have this, well, it starts with a short, that would be 2 bytes, then I'd have 2 bytes of padding, then 4 bytes for the int, then 2 bytes of padding, then 2 bytes for the short, then 2 bytes of padding. So each of my S3 structs here are 12 bytes, and 4 bytes are lost to padding. And then each of the structs, well, since they're all aligned and everything like that, an array of them would just go every 12. So every 12 bytes, that would be how often the structs are if you just did a big array of them. And yes, of course, the elements, the order of elements matter. So the other one, if I didn't do short int short, well, I could actually save in total 4 bytes. So if I just did short int, then C rules, it will apply, it will store everything in the exact same order as you declare it in. So in this case, I would have 2 bytes for I, 2 bytes for j. That satisfies all of the alignment requirements. And then I would have 4 bytes for the int. The whole structure would be aligned to a 4-byte boundary. So I can actually save all that padding. The structure is now 8 bytes instead of 12. So way more cache friendly, everything like that. Things are way more packed together. Generally, you want to reduce padding as much as possible. So it's good to know these rules if you have not seen them before. So that's how structs are laid out in memory if you do use a struct. The order you declare them definitely matters, and they're always in the same, laid out in memory in the same order you declare them in. So you might also want to put, along with keeping track of the alignment, you might also want to make sure that, hey, if my struct is absolutely humongous, 2 fields that are used together are declared close together because that means they'll be stored close together, which means they'll likely be in the same cache line, which means your life will be great. So, memory management. Everyone loves using malloc. So, malloc, you tell it a size. If it's successful, returns a pointer to that new block of memory, at least size bytes. Size is 0, returns null. If it's unsuccessful, it returns null, sets error no, and if you have written your program well, you check for malloc. Everyone's checked for malloc errors, just like everyone checks for errors from printf, correct? Yeah, that's what I thought. Well, if malloc starts returning null, you're probably in trouble anyways, so your program's probably going to crash anyways, so don't worry about it, I guess. Should probably still check and crash it yourself, but probably more useful than checking for printf. Typically, malloc returns double word align addresses. So on a 32-bit machine, word is 4 bytes, so it returns 8-byte aligned things. 64-bit machine, 16-byte. That's just the worst alignment you could have. That's generally the reason for that. We'll see once we get into the algorithm a little bit why we might also want double word aligns if we're only keeping track of blocks of word sizes at a time. So the other things we have to do that you'll be doing for lab 3, implementing free, so that it should return, shouldn't return anything. So it should just free the memory pointed to by P back to the pool of available memory so it can be reused, hopefully. P has to come from a successful call to malloc or realloc. Realloc, right, you give it a pointer and a new size. It will either shrink it and grow it and leave the first few elements the exact same, even if it grabs a new block of memory and it physically moves it. It has to do the copy. So we've probably all used that before whenever we were resizing an array or something like that. Although you could use realloc array to make it a bit more obvious. So this is a malloc example. I assume you don't actually need this. Just malloc some space, initializes it, reallocs it so it grows it, initializes the new elements, prints them off, frees it. I don't have to show this, right? Everyone's fine. Again, not too sure why this is here, but if you want me to slow down, let me know. All right, we're all right. So, some assumptions we will make. Memory is word addressable, so each word can hold exactly a pointer, so we'll just assume 8 bytes. And then malloc returns at least word align addresses. In practice, malloc returns at least double word align addresses. And well, now with x86 CPUs, it will do the worst alignment, which is quad word aligned, but we'll just assume word aligned for this. So each of these little blocks here, they represent a word or 8 bytes, and those are the blocks we will use for our allocations. So you might think it looks something like this. You either have an allocated block or a free block, and malloc is essentially managing all these blocks of memory. So the shaded ones are all allocated words. So this would just be 4 words altogether, 8 bytes each. So this is an allocation of 32 bytes. And then maybe there's 2 free bytes here. You know, we have some allocated for another malloc allocation, some more free blocks, so on and so forth. So, some examples could look like this, assuming we're just allocating words at a time. So the size of a pointer or void star is just the size of a word. So that's just one box in this diagram. So if we do malloc of 4 words, then maybe our malloc algorithm will say, hey, let's pick these 4 blocks of memory for this allocation. Then maybe you come along, you say, hey, I want 5 more words. So we pick the next 5 bytes to return that are all contiguous. Then they malloc 6. So, okay, you pick the next 6. Then we free P2, whoops. Then we free P2, which is this red allocation here. So we free it. These 5 bytes are now available to use somewhere else. And now we have another allocation of 2 bytes. So we get to decide where we put it. We could put it here, split up the 5 blocks into a 2 and a 3. So we use 2 for the allocation, 3 are free. And we still have this 2 block at the end, or we could have used the 2 block at the end. Up to you. That's what you'll be doing for lab 3. So some other constraints you have if you are malloc. You have to assume that the programmer, whoever is using malloc, is insane, basically. They can do whatever they want. They can issue arbitrary sequence of allocation and free requests. And free requests must correspond to an allocated block. Aside from that, there are no other rules. So if you're an allocator, if you are the one implementing malloc, you must respond immediately to an allocation request. You must give them memory as long as you can. You can't reorder anything. You can't do anything special. You have to allocate from blocks of free memory. You shouldn't try to overlap your request. Otherwise, you will cause every application on the face of the planet to break. That is the minimum requirement, is that it gets back memory that is not used by anything else. And they have to align blocks so they satisfy all the memory requirements, typically why they're at least double word aligned. You can only manipulate and modify free memory. You won't play with the user's memory or screw up their data under any circumstances. And because this is C, as soon as you give them back a pointer, you can't move the allocation once they're allocated. Your decision is essentially permanent. You can't redo, you can't move the memory around unless they realloc themselves, but the default case is you can't compact anything. They have a pointer, they get to use that pointer, it's valid until they call free on it. If you are Java and everything's a reference, you can do this. You can compact things. We'll talk about the garbage collector a bit later in another lecture. But if you're C or C++, all your malloc decisions are permanent until they actually free them. So if we're writing a good malloc in free, well, we want good runtime performance. Whenever we call malloc, it shouldn't sit there and just decide for 10 seconds. Otherwise, you probably won't use it. Even if it picks the smartest, this is impossible. So ideally, it should take constant time. Not always possible, but it should, of course, be as quick as possible. So hopefully, it doesn't scale linearly with the amount of blocks, like the amount of blocks you're actually using. Otherwise, your performance will probably be really bad. And the other conflicting goal is that you should have good space utilization. So you shouldn't waste a whole bunch of memory. You should be smart about where you fulfill the request in memory, because you want to minimize fragmentation, which is just another fancy word for wasted space. So usually you have a trade-off between the two. The smarter you make it, the better you'll be at space utilization, but it might take longer to make a good decision, so you'll have worse performance. So there is a bit in a give and take. And in lab 3, it slightly prefers you to have better space management than pure performance. So I think the split for lab 3 is like 60% space utilization, 40% performance. So one extreme example of an allocator that is very, very, very quick is malloc could just find the next available n free blocks and return that memory, and then whenever someone does free, you go, sure, and you don't do anything. Is that valid? Does that satisfy all the constraints? Yeah, sure. Great time performance, really poor space utilization because nothing will be reused ever. It kind of looks like what happens with a stack, right? So unlike a stack, we can't free everything because we don't know the lifetime, so we can't just free everything all at once. But perfectly valid thing to do. That actually has a name. Don't know why it's not on the slide. The name for that allocator is called a bump allocator. So it just bumps up memory every single time. Bump, 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 bump. Only bumps, no dumps. I don't know. I don't know where I'm going with that. So, some performance goals. Throughput. Probably want good throughput. So you'll have some sequence of malloc and free requests. For lab 3 especially, you're given traces from real programs of their allocation requests, and those are what's used to judge your implementation of malloc. So given some request ARD, which would be either malloc, a realloc, or free, you want to maximize both throughput and peak memory utilization, which, like I said before, often conflict. So throughput is simply just the number of requests per unit time. So if I have 50,000 mallocs and 5,000 mallocs and 5,000 frees all in 10 seconds, that means I have a total of 10,000 operations over 10 seconds. So if I just divide them, that is 1,000 operations a second in throughput. If I want to actually evaluate peak memory utilization, well, I need a few numbers. The first one is aggregate payload. That's denoted by P, which is basically at any given time how much memory has the user requested. So it takes into account freeing. It's the amount of memory actually requested through malloc at any one given time. So if you free, that would reduce it because you're not using that pointer anymore. This is what the programmer actually requested at every time instant. The total heap size denoted by H, K at different times because you will grow your heap, probably will never shrink it. And then peak memory utilization is just after some number of requests, you just find out whatever the worst case was. So whatever the maximum amount of memory they wanted to use is divided by the amount of heap space you use. And why high watermarks? Well, because it wants to keep track of the worst case scenario, make sure that you're actually reusing your memory if they go ahead and free a whole bunch of memory to make sure you don't have that fragmentation issue. So, speaking of fragmentation, why do you not want fragmentation? Well, it's basically just wasted space. So, comes in two forms. Again, kind of review from 344. Internal fragmentation is unutilized space, like within an allocation, within the blocks, which would be padding. It's just wasted space within the structure. Can't do anything about it, really, if you're the memory allocator. And then external fragmentation, which is the memory allocator's concerned, which is basically space in the heap that I cannot use anymore. So I can't fit an allocation in, like I have too many holes in memory, too many blocks, too many gaps that I can't actually use for an allocation, so they are effectively wasted space if I can't actually use those bytes for allocations. So internal fragmentation, again, if I have, in this case, a 32-bit CPU for some reason, if I have a 4-byte word size and I malloc 13 bytes. Well, the payload is 13 bytes. That's how many bytes you requested. But your returned allocation is going to be 16 bytes because it would be 4 word-side requests, and this would count as just padding. So that padding would just be deemed as internal fragmentation. So that only depends on just previous requests, really easy to measure. And internal fragmentation, it's just there's a minimum size for our allocator. If we assume we only deal with word-sized blocks at a time, and we have alignment requirements, then any data we use that's wasted to fulfill alignment requirements is lost to internal fragmentation, or if our size of a block is different. So if we use some space to keep track of our allocations, that will actually affect the heap size and peak memory utilization, but not internal fragmentation. Internal fragmentation is just has to do with the size of the request by itself. So external fragmentation is wasted space between the blocks. So I just don't have enough, like I have enough memory to do it, but not a single contiguous block large enough to fulfill the request. So if I just allocate things in order, so four blocks, 4 word-sized blocks, okay, I allocate them at the beginning, then 5 word-sized blocks, allocate them at the next 5 elements. Then I have an allocation for 6 come up, and then, well, I put that at the end. Now, if I free P2 again, I have 5 blocks free here, 2 blocks free here. But now, if someone tries to allocate 6 blocks, now I have no room for it, assuming this is the total size of my heap. I have, 7 blocks in total available, but I can't fulfill a single allocation for 6 bytes because I don't, or 6 blocks, because I don't have 6 blocks contiguous all at once. So the external fragmentation depends on future requests. If I can't fulfill any future requests, then that is external fragmentation, so it's a bit harder to measure. Because in this case, if the user requested, I don't know, even 5 bytes or 2 bytes or something like that, I could satisfy the request and be all good. All right, so how to actually implement malloc stuff. So basically, well, a few things we need to keep track of. We need to keep track of which region of the memory or of our heap is free. So also when we're asked to free an address, we also need to know how many bytes to free. Part of the API free, it just gives us a pointer, so we need to actually have that information stored somewhere. So we need to keep track of how many blocks to actually free, and we also need to keep track of, well, how do we even keep track of which blocks are free? And then for allocations, well, we have to figure out which blocks are we going to use for an allocation, because we might have lots of possible scenarios. So if we malloc space for only a single block, well, which one do I use? Do I use one of these 3, one of these 2, or one of these 2? So I have lots and lots of different options. Some are better than others. So if we want to know how much to free, the easiest thing to do is to just keep the size of the block in just the word preceding the block. So this is often called a header. So if you just back up a little bit of information, you can actually use that to actually store some information about the allocation. So it's right next to the allocation whenever they need to free. It's right there in memory if we take care of the caches and everything like that, and we're all good. So this has a bit of space overhead. So for every allocation, we need an extra word. So in this case, if we just have an allocation, so if we malloc space for 4 words, 4 blocks of memory, well, then we would return a pointer to the beginning of those 4 blocks of memory, and then the block right before it, we might store the size. So we would have to store the total size, so the size of the allocation, which is 4 plus 1, that keeps track of how big this header is. So in total, we would keep track of, hey, 5 bytes for this allocation. 4 for it, and then 1 for the header. So that's what it would look like. And now if we free, oh, well, we could just back up 1 and say, okay, well, the next, including this block, this header block, the next 5 blocks are all free. I can reuse them for another allocation. Good? Yeah?
All one-word blocks would become unusable then, right?
All one-word blocks would become unusable.
Oh, sorry. If they're sandwiched between, like right after the second horizontal bar there, that like one block.
Yeah, so if I have a header file, right, and I assume that I can only allocate 1 block at a time, there'll be at least 2 words away from each other now, right? So this could also be a reason why it's at least 16 bytes requirement, because they'll have 1 block for a header anyways. All right, so how to keep track of the free blocks? Well, it's lists. Everyone loves lists, right? So there's a few different ways. You could just do implicit. So implicit, if you're keeping track of the size field, well, that's basically a list, right? If you keep track of like the size of each allocated and freed sequence of blocks, well, that's like a list. So if I know this is free, well, then my next allocation would be at 5 blocks away. So it would be here. I could check. We'll see how we actually keep track of what's allocated, what's not. But if this is allocated, I can be like, okay, well, what's my next big block of memory? Skip 4 blocks and be like, oh, okay, well, now this is 6. I have 6 blocks free. And if I want to see what's next, I can skip 6 ahead. Then I have 2, so on and so forth. Another way of doing this is, well, I still have to keep track of the sizes, but maybe I don't want to leap over every single allocated or unallocated block, because generally, if I'm mallocking somewhere, I need to find some free space for it. I don't really want to jump over a bunch of allocated space. That's just a waste of time. So the other method is to use an explicit list. So in the free block itself, that's basically free real estate. So since that's free real estate, the free block itself, I only really need to keep track of the size. So I can just use that memory to instead point to the next size for the next free block instead of just the next possible allocation. So free real estate, boom, I can just hop over to the next free block. It's 6. Then the first word there would just be a pointer to the next free block. And now I just have an explicit list of all of my free blocks. And then method 3 is just segregated free lists. So I could take that idea and take it to the extreme. So if I really wanted to, I could have different free lists for different size allocations if I really wanted to optimize things. And that might be a good idea to do for the lab. Ooh. So first method is the implicit list. So we need to keep track of whether or not a block is free or allocated. So I can be a little bit clever about this and then use a single bit that is part of that size field, because, well, I know that the size will always be a multiple of 2. So if it's a multiple of 2 all the time, then I don't have to that means the lower bit will always be 0, which means it's also free real estate. So I can use that bit to keep track of whether or not that block is, or that sequence of blocks is allocated or not. So what I can do is just mask it out. So I can use the least significant bit to store 1 allocated, 2 or 0 free. And then whenever I get the size, I just have to make sure to mask out that bit if it's actually set, so it doesn't mess with my sides, and I always get even slides. So we could do just an AND with the knotted just 1, so that would flip every single bit. So that would just do an AND with all 1s and the lowest bit as 0. So that'll essentially just make the lowest bit always 0 and then keep the rest of them as they are. So we write the size. So now the format looks like this. We have our size, which takes up the remaining, in this case, 63 bits. And then our allocation, that's just one single bit there that we'll keep track of. Again, is this sequence of blocks of size allocated or not. And then the payload, that is actually memory used for the request that we should never, ever touch. So questions about that? Clever thing to do, right? We just mash stuff in, reuse some bits. Lots of fun. So if we have this implicit list and an allocation comes in where we have to find a free block, well, we have to figure out which one to actually use for the allocation. Well, part of your malloc implementation, since you have an implicit list, you know where your heap starts, so you know where to start looking for free blocks. So there might be multiple blocks that can fulfill an allocation, so we have to have a way to pick from them. So the first thing to do is first fit. So search from the beginning, choose the first free block that fits the allocation. Works. So it takes linear time in the number of blocks, both allocated and free, which should be setting off alarm bells already. And in practice, even if you do this as fast as possible for the space utilization, it causes a bunch of splinters or some fragmentation at the beginning of the list. And especially if it restarts at the beginning of the list again and it has a bunch of free spaces, you could do some easy optimization here where since you went pretty far and found a free block, you could just save where you found the last free block if you wanted to try and speed it up a bit. But practice, generally a fairly bad idea. But that's what next fit is. So like first fit, just search the list from the end of the previous search. Don't bother searching from the beginning again. But if you simulate this, again, no one really uses it, but fragmentation is generally worst if you do next fit as well. Best fit is that strategy where you search the list and instead of just finding the first thing that fits it, you try to find the closest size that fits. So you're a bit more selective, you're spending more time to actually find, hopefully, a better allocation. So this will, if you simulate this, keep fragments pretty small, usually helps with fragmentation. But of course, we have to scan every single thing, every allocation, which is going to be way slower than first fit or next fit. It has no end early condition. So if we are doing some allocation from a free block, right? Let's say we're just getting some block of memory. Then say if we're doing next fit, we're here. This doesn't quite fit. So this is all allocated now. So we have an allocation come in of 4 words. So the next free block we would look at, we'd take this, jump the size, and then here we would find a 8-word block size of free space. So our allocation does not need all of that space. So we would split this huge free block into the 5 blocks we need for this allocation. So 1 word to store the size and allocated or freed. Of course, say it's allocated. The 4 blocks for the allocation itself. And now we have to make sure that, well, we split that 8 into the 5 and the 3. So now this is a smaller free block. So it has 3 blocks, it's free, yada, yada, yada. Everyone all right with that? Makes sense. So if we need to free a block, it's really easy in the simplest sense if we don't want to do anything clever. So if we have this allocation P here, right, if we say free P, all we have to do in our implementation is look backwards a block. That gets us our header. And then we can just flip that bit from allocated to not allocated. And then we're done. So if we did this, it works, but we could be a bit smarter about this, because now if someone asks for a 5-block allocation, now we can't fulfill it even though there are 6 blocks in a row there, because the naive algorithm would just search, oh, well, if they request 5, I actually need 6, 1 for the size, 5 for this. So can't fit it here, can't fit it here, can't fit it here. It's not that clever, but since these are two free blocks beside each other, I should just consider that as one big free block, right? So that is the method or algorithm we call coalescing. So I should merge any 2 free blocks that are beside each other. So coalescing is basically just joining 2 free blocks together. So in that case before, if I free, what should happen is, well, I'll look up my allocation, look at the size of my allocation by going back, saying that it's free now, and now I should look ahead 1 and look behind 1 and see if I have to coalesce or merge 2 blocks together. So there might be different options here. So the one after me, well, that allocation could be free, could be allocated. The one before me could be free, could be allocated. And also, if this is my linked list, going backwards is a bit hard, right? So I have to probably do something about going backwards if I have to handle coalescing, because it's not always guaranteed. I only need to coalesce with whatever is my next block. So, yeah.
So, like, how do we actually know if the previous block is free? Do we need a doubly linked list for that?
Yeah, so that's the next thing. Basically, we need a doubly linked list. So they call it a bit different thing. So this was in like the 70s. So they call it bidirectional coalescing. Basic idea is the same thing. We have a doubly linked list. So what they do is, since it's an implicit list where they just use the size to jump forward, what they do is just replicate that size at the bottom of the free blocks, or sorry, just replicate the size at the end, and then that tells us how many blocks to go backwards. So now we can, like a doubly linked list, traverse the list backwards. So we put the size at the beginning and at the end. So now if we want to go backwards, so from the header file, you would just read back 1 unit or 1 block. That will tell you how many it's replicated. So it tells you how many blocks to go back to get to the next previous, and we can actually jump the list backwards. So now we can go forwards, and we can also go backwards. Otherwise, it's exactly the same thing. Again, we just replicate that size block, and now we can go backwards. So we have a doubly linked list now. Fun. So, yeah.
So, but does that then reduce the actual size of the data that we pulled in every block? Because now we have like 2 blocks that's just hold the size of the
Yeah. Yeah, so now we have a bit worse space utilization, because now we're using 2 blocks or 2 words for every single allocation, no matter what. And this also before, where it said like things were always multiples of 2, well, now they're definitely multiples of 2, because we have a word before, a word after, and then malloc has to return everything aligned to a double word. So these are definitely always going to be even numbers. Yeah.
Is there any way to escape that at all, though?
any way to escape that at all? You sure? Yeah, we could escape it if we stored the list somewhere else, right? We could store the list somewhere else. We need to store the information somewhere. We could probably do slightly better than this, but this, I mean, most things are a trade-off, right? We're trading off more space so we can actually go backwards a lot faster. So, like with everything, there's a trade-off.
So if our data size is on average sufficiently big, is it really worth trying to design something better?
Yeah,
If
so,
our data size is like 4 kilobytes even.
yeah,
So small. 2 segments of like words is not gonna.
yeah, if the allocations are big, doesn't matter, right? This might be really bad if people just requested a single byte at a time. Like I want a byte, I want a byte, I want a byte with alignment requirements, and then this, what? Da-da. So that's 32 bytes each allocation, and you use one of those, so 31 bytes wasted every single time. So generally, with most algorithms, you do something special for small allocations because you don't want this to happen. And we'll go over some of the options we have, but you can think, sky's the limit of this. You can think of whatever you want. But this is just one example. If we have an implicit list, how to actually coalesce blocks is what we're doing right now. So we have a few different situations. If we consider the block being freed and then the previous and the next block, there's 4 situations. Either we're sandwiched by allocated blocks, and in this case, if we're sandwiched by allocated blocks, do we have to coalesce a damn thing? Hopefully not. If we're sandwiched by an allocated block previously and a free one next, then we have to coalesce. Same thing if the previous is free and the next one is allocated, we have to coalesce with this. And then if both allocations on either side are free, we have to coalesce with both of them. So this is case 1. This is assuming, so this is the allocations. So here, each bolded box is a single allocation. So we have one word here for our size with allocated yes or no. So here the size would be M2 or M1, sorry, and it would be allocated. So we have a 1 here. And then since it's the bidirectional one, it has a header it also has, I guess, a footer. So that's replicated. So the size is M1 and it's allocated. And then this middle allocation, that's what we're assuming we're freeing. So we have an n size allocation here. It's allocated. Since we're freeing it, we need to flip those bits from a 1 to a 0. And then the next allocation here, size M2, and it's allocated. So if we coalesce this one, what should our final thing look like? Well, this block should stay the same. It's allocated, it's being in use of something, we shouldn't change anything. Same with this block M2, it's in use, we shouldn't change anything. So all we have to simply do is just flip our bits, both the header and the footer, to just be unallocated, and now those n blocks, n minus 2, I guess, blocks can be used for another allocation. So that all right, and we can do this in constant time. We only have to look previous and next. All right, the other case, slightly boring. So we're freeing this. The M1 is allocated. M2 is free. So this case, we have to coalesce, right? So what will our final result look like? Yeah.
We'll have like n plus 2, sorry, n plus m2 freed, and then same thing at the bottom.
Yeah, so here we can't touch M1, so this will be M1, 1, M1, 1. And then since we're coalescing these blocks, since the size is including the header files, including the header blocks, including everything, our new free one, we're coalescing with this M2, so our new size that is free is N plus M2, and that whole thing is free. So it's just going to look like this. So we have N plus M2 all free, so that bit is 0, and we have all that free space. Yeah?
Since we lose two headers like in the middle, shouldn't we increase the amount of free space?
So this N and M2 include the header space, yeah. So if we're using two headers, this space in between, we can use N minus 2 for the allocation. All right. So the next case, this should be boring, right? So, the one previous is free now. What does it look like now? Well, hopefully this is not that exciting. The new coalesce block, it's of size M1 plus N, and it's freed before, and we don't touch M2. Magic. Now, the tricky case. What about if it looks like this, where either side of you is free? What should it look like at the end? Well, if both things are freed, the entire thing will be free now. So now we have N plus M1 plus M2, and the whole thing is free. So we have a big block of memory. So the way this works and the way it's constant time too is it always merges whenever you free. So we're guaranteed to always get a sequence of allocated free, allocated free, allocated free, allocated free, and the frees are as big as possible. So this is a good thing to do, help us keep track of however big our entire free region of memory is. Otherwise, we could get confused. So some summary. So the placement policy, how to find the free block. We could do first fit, next fit, best fit, or pick your poison, random fit. Sure, why not? You have the coalescing policy, so how to insert a block during a free, or how to keep track of all the free blocks. Immediate coalescing, you just coalesce adjacent blocks whenever a free is called. You could defer it if you wanted, because, hey, maybe I'm merging two things together and then immediately splitting. Merge, split, merge, split, merge, split. Maybe that wastes a lot of time. Maybe for performance, you would prefer not to do that and just hopefully reuse that without having to split again. So maybe you try to defer it as late as possible. I'll just leave it in some state, and then whenever I'm actually allocating space and I can't find enough space, maybe I start coalescing then. Or maybe if I reach a threshold, then I start coalescing. So I already spoiled it. Why might it be beneficial? Again, don't want to split, coalesce, split, coalesce, split, coalesce. It's just wasted time. All right, so implicit list. Oh, yeah?
Sorry, going back to when you're talking about placement policies, do there exist any placement policies that will try to predict the next block that's going to be freed?
You could try and predict the next block that's going to be freed. Generally, that
Wouldn't really help?
yeah, for most memory allocators, typically doesn't really help. You can do other things.
I guess what I'm wondering is, like, if I know for a fact that some block is going to be free, given some time, then I might not want to place my new block right next to it, because if I can place it somewhere else, then my place that's freed would be bigger and then more able to be utilized by something else.
Yeah, generally, if you get in the case where you actually know the lifetimes and stuff, there are some memory allocators you can hint lifetimes.
Okay.
And generally, if you know it as a programmer, you start managing your own memory, or you do some other technique that we'll show in the next lecture. So there are different things to do. Generally, if you know your own lifetimes, you can do much better. General memory allocators, it has no idea what the lifetime is going to be. There are some heuristics you could probably come up with, but they might be wrong. Yeah?
Sorry. Did you answer the question at the bottom?
Yep. Yeah. Anyone help? What's the answer to the question at the bottom? Why might I want to not coalesce immediately? Wow, no one's helpful here. What? Yeah.
Because if you wait a bit, you can basically do all your coalescing at once and save time.
Yeah. So what about if, let's say we do this, right? Let's say these are all, I don't know, 4 blocks or something, right? So I coalesce them together to have a giant 12, and then I get an allocation for 4 to come in again, like the same size of all those. Then what do I have to do? I have to split this again, right? Well, if I didn't split it, they're already the right size. I would just flip the bit and then just carry on my way. So if I just defer coalescing, I'm less likely to have to split it again, maybe. Yeah.
Probably weren't allowed to defer any operations, though.
You're not allowed to defer any mallocs. So yeah, the not deferring is so if someone calls malloc, you have to give them memory. But however you want to manage memory, make your decisions, you can do whatever you want, as long as whenever they ask for memory, you give them memory. And like the bump allocator, I mean, you could make poor decisions, you could not free, you could do whatever you want. All right, so for implicit lists, the implementation is simple. Everyone loves lists, so they're not that bad. So allocation, kind of slow, linear in time of free and allocated blocks, which is really bad. You shouldn't really care about allocated blocks. Free is constant time, even with coalescing, as long as you don't defer it. And then memory usage, that depends on the placement policy. Again, for this one, you do first fit, next fit, or best fit. In practice, yeah, you're not going to use it because linear time allocations, and it also depends on the number of allocated blocks, which is really bad. And splitting and coalescing, that's used by other allocators. It's a good thing to know. But this implicit list generally, I mean, it works, but it's not going to be the greatest thing on the planet. So the second method is the explicit list. So this is the idea where if there's a free block, what we do is we actually, instead of having an implicit list that keeps track of allocated and free blocks, we just use the free blocks to store the next and the previous pointers on the blocks themselves, on the free blocks themselves. So that way we have just pointers. We have a free list. All the elements are free. So we don't actually have to scan any of the allocated memory. We don't touch it. We just skip over it. So it's a lot faster, especially if someone's been using the allocator for a long time and they allocated a lot of space. So typically this is doubly linked for coalescing reasons. So they just call next a successor and previous a predecessor. Links can point anywhere. It doesn't have to necessarily be to the adjacent block, right? After some time, it might get slightly messy, but as long as you keep track of all your pointers and you don't do anything wrong with pointers, you're all good. So here, again, they still have those boundary tags for coalescing purposes, but they don't use them for anything aside from coalescing. To actually do an allocation, I would actually just go through the explicit free list that's also stored on the blocks. So if I have to allocate from the free list, well, if initially I just have a block where I just have one single giant block of memory when I start my malloc, right? So I'll probably have some global variable or something like that. That would be the state of your allocator that has the predecessor or whatever's at the head, and then whatever the final successor is, or whatever's at the tail. And initially, they both point to the heap, which is just all free. And then after you allocate it, well, you need to split that. So this space would be used for the allocation. You just give the allocation black. And then Now your predecessor and successor, or your next and previous, however you want to call them, now just point at that smaller block of free space and da-da-da. And in this case, allocation time will be linear in the number of free blocks instead of total blocks. You just have more pointers, which is always more fun. Everyone loves pointers. All right, so if you free from like just an explicit free list, then you get to decide, hey, well, since I have an explicit list of frees, where does this free block get inserted in the free list? So you can do whatever you want. You could do last in, first out. So you put the freed block at the beginning of the free list. That means whatever you freed latest is probably going to get reused again, maybe, and that's simple, constant time. If you actually simulate this with real programs, then fragmentation gets worse than if they were just in address order, but of course that's going to take more time. If you have address order policy, you could insert the free blocks so that they're always in address order. If you want, that will require a search or require you to go, maybe if you pick wrong, up to the length of the list. But you might get better fragmentation with this, so it's just something to try and see. And lab 3, you're graded on traces. The traces will always be the same, and you have all of them. So if I'm freeing with last in, first out, so my free list initially points to some free blocks X and Y, then here I'll assume that this is just my memory, whatever is contiguous, because I'm trying to coalesce in this example. So self is the allocation that we are trying to free. And then, well, if there's allocated blocks on either side, that means no coalescing or anything like that. So if I'm freeing this, if I have last in, first out, all I want to do is make sure that my free list now points to this free block that I just freed, and then its successor would point to X. So it's just normal add to the front of the list, as you should be familiar with. So we take the next pointer for this block that we are freeing, pointed to whatever the free list pointed to before. Then I would set the free list previous to the new free block, since this is last in, first out, and then make the free list now point to the block I just freed, and then I have no predecessors. I'm at the beginning of the list. Now, how do I coalesce? It's basically the same thing as before, right? So same thing as before. I'll still have the header. I'll still have like the size at the header and the footer. So it's the same thing as before. I just have to make sure that my linked list is proper. So here I have to take in consideration the linked list, because my next element, right, whatever is contiguous to me in memory, would be in the free list, so it would have pointers to like a Y and a Z. So I have to make sure that when I coalesce, I don't screw up my free list. So in this scenario, right, I need to coalesce self with this free block, but since I'm coalescing that block, then it should no longer be in the list anymore. So what I have to do is splice out this free element from the list. So its previous would have been Y, Y's next would have been to it, its next would have been Z, Z's previous would have been it. So I need to fix it up so that just Y points to Z. So I'm essentially removing this free block from the list, and then I coalesce it, and then at that point, then I add it to the beginning of the free list. So does that make sense with everyone? Same idea as before, same coalescing rules. I just have to make sure that I don't screw up that free list. So has the other cases here where, hey, the previous one is free. Well, same thing again. It will point to some X and a Y. It will have a previous and a next. So basically, I splice out this free block. So I set it so that X and Y are now linked to each other and to do not reference this F at all, then I coalesce that free block with whatever was beside me, which was the allocation or the deallocation I'm just doing right now. And then since it's last in, first out, I now point to this block. So same idea as before. Now, if both things are free, that's a lot more pointer operations, but it's just more fun, right? So I have to splice out the block before me that I'm trying to coalesce, and I have to splice out the block after me that I'm trying to coalesce. So I have to essentially remove both these entries from the free list. So in this case, I completely remove them so that X points to Y, Y points to Z, and then the reverse is also true. And then this giant block of memory is now all coalesced, and it goes at the beginning of my free list. Any problems with that other than implementing it and then having an error and then trying to debug it? Yeah, conceptually, not too bad, but that's a lot of pointers. So, summary of this, comparison with an implicit list allocation is going to be a lot better, especially if the memory is really close to full or you're close to using all of your heap space. And more complicated since you have to splice them in and out. You're keeping track of that free list and dealing with a hell of a lot more pointers. But other than that, other than making your life more complicated, overall, it is a much better strategy. And the other thing we could do is have segregated free lists, which means we have different free lists for different sizes of allocations. So maybe you have a different free list for small allocations, maybe different types of objects, and that's in the next lecture. So what it basically looks like is if you have a segregated free list, maybe you have just one list for each different size of allocation. So maybe you have a list for small allocations of 1 or 2 blocks, maybe a list for 3s, maybe a list for 4s, and then you don't ever bother coalescing or doing anything like that. You keep them split for the same reasons as before. And then once you get to 5 and 8, right, you can assume that people will mostly use powers of 2 and special case the other ones round up. So typically, they'll use size classes for typically every power of 2. Some of them might make it for 3 or 4 or maybe 5, but 3, generally kind of unusual, but maybe people use memory weird. You might have malloc 3 bytes in 105. I don't know what you did. Who knows what people do? They're allowed to do that. So if you have larger sizes, but typically you just do powers of 2 in general. So if you did very simple segregated storage, you could have all blocks have the same size. So whenever some allocation comes in, you could round it up or just make sure it fits in a range. Then if you need to allocate a block of that size, if the free list is not empty, you just allocate the first block on the list. You don't have to split. You know the sizes of it. It fits exactly. And if the free list is empty, so at that point, you grow the heap, and then you create a new free block of size n based off how much you expanded the heap, add the blocks to the free list, and then allocate the first block in the free list. So the idea behind this, again, is kind of like that deferred coalescing, but in this case, you don't even defer coalescing, you just never coalesce. You just have different sizes. That way, don't have to bother to coalesce ever. And whenever you free a block, easy. Again, no coalescing, just add it back to the free list. Nothing else you got to do. Yeah?
For coalescing, then you also need to manage, if you coalesce 2 blocks that are beside each other, you might need to move it to a new class of block size, right?
Yeah, but for this one, we wouldn't bother coalescing. But you're right. If we wanted to coalesce this, then yeah, we might have to move it to a different class size. And generally with this, this is the simplest thing we could do. We just don't bother. We just never coalesce, just have different lists of different sizes and always keep them the same. Don't want to bother coalescing. Screw that. Remember, like I said before, the best optimization is what? Do nothing. The best optimization is to not do anything. So if we cannot do anything, that's the best one. Probably shouldn't quote me on that one though, because it could get in trouble. So, some advantages. You get nice constant time allocation and freeze. So they're all the same size. You don't have to bother splitting or coalescing. Generally, per block memory overhead, the block size, you don't even need to maintain the block size in the header. Since everything's the same size, why would you store the same thing 10,000 times if they're all the same and you already know they're all the same? Why the hell are you even bother? So that would actually save space for the smaller allocations. You can fit them in blocks right next to each other. But some disadvantages of they can lead to internal fragmentation a lot, since you generally round it up to the next size, so you don't have a billion lists, because that would also count against your space utilization. And also can lead to very high external fragmentation, because we're not doing anything clever here, right? We're not shifting any sizes or whatever. So if some program used 10,000 4-byte allocations and then was like, screw that, I'm done with 4 bytes, and then used everything as 8 bytes, well, all that memory we use for all the 4-byte allocations in the simplest strategy will never be reused. We don't move blocks up and down size classes or anything like that. No coalescing, no nothing. So in this case, all the blocks in the list, they lie within the same size range, even though they could have different block sizes. Again, fragmentation. So if I do best fit and try and do a bit better, if I allocate a block of size n, then maybe I try to search the appropriate free list for some block without making a different category or something like that. So if I find some space where it will fit, maybe I split it and then move that split one to the appropriate free list for that allocation size. If I don't find a block, maybe instead of asking for more heap memory, where I try to have better space utilization, maybe I go the next size up and see if there's anything free there, and then block and then split that and then move it in allocation sizes. And then if I still can't find anything, then as a last resort, I grow the heap. And then to free a block, maybe it's the idea you had before, coalesce, I might have to move it to a different size. So some advantages of this is fragmentation might be a lot better than the simple case, since things can move around, mostly due to being able to move it around through splitting and coalescing. Fragmentation, similar to best fit for just the free list. It's going to be faster than not having segregation at all. Doesn't require an exhaustive search. I at least know what classes to search. I'm not bothering to search any allocations I know won't fit. But some trade-offs are doing the allocation is going to be slower. It has more things to go over, more different lists. And splitting and allocation can really increase the search time, especially right if we reuse that gain. But like before, we could use the idea of deferred coalescing. But the best thing we can do is, anyone remember me talking about buddy allocator? So buddy allocators, yeah.
Is this also called slab allocator or no?
No.
Oh, it's different.
Yeah, slab's a bit different. I think it comes up too. But they're two different things. So buddy allocator, it's basically segregated best fit, but it uses powers of 2 to actually make the coalescing happen in log n time and a bit faster. So everything has fixed size blocks, but now all our fixed size blocks are powers of 2. So if an allocation request comes in, we round up to the next power of 2. And what we do is, if the free block of that size is not available, we find the next power of 2 up, and then we can recursively split it in 2 until we exactly fit our rounded up allocation size. And then if we free, the idea is, since we're splitting in 2s, every time we split in 2, we have what we split and then the other one. The other one is called your buddy. So you always check with your buddy to see if you're free or not. So that's why it's called the buddy allocator. So you can easily figure out who your buddy is by just flipping a bit. So if you know the size and you're the buddy at that size, you know what bit to select. And then if you're bit 1, your buddy's bit 0. If you're bit 0, your buddy's bit 1. So uses power of 2. Easy to figure out who your buddy is. You might not know your buddy's buddy, but you know your buddy just by flipping a single bit. So how that works is, assuming we just have this giant region of memory and each column here is a 64K, might be a little bit hard to read. So initially we have, what's that, 2 to the 8 different 64K blocks. And if we allocate a 32K, well, we round that up to the next power of 2, which would be 64K, and that would only use a single block. So we would take all of these blocks and then just recursively split it in 2. So we take this 2 to the 4, split it off into 2 powers of 2, then take that 1 power of 2. Since we're doing it recursively, we only do it on one side. Whoops. Split it off into 2 powers of 2 to the 2, which is 4. Then split that off, that 1 4, into 2 2s. Then split that 2 into 2 1s. And now we have enough for that 1 allocation. Again, you might just have to look at the slide and download it because that does not look great. But otherwise, if a B allocation came in for 66, that's supposed to be, also that's very neon, then we round up, it's 128. So we would scan and see that, hey, we have exactly a block that's 128. So we would use that for the allocation. Then if we allocate 35, that's round that up to 64. So one of our blocks already fits, so we would put it there. Then, we allocate 67, have to round that up to 128. So we would have to actually split this block here, split it, it fits. And then whenever we free this block, well, it's just free. Its buddy is not free on either side of it. There's nothing free, so we wouldn't coalesce it. And then whenever we free D here, well, say the address of D, it lives at 256K, which is this address. And if we know the size of the allocation, the power of 2 was 128, that means it's this bit indicates who your buddy is. So, whoops, this bit indicates who my buddy is. So if my address is 1 and a whole bunch of 0, it means my buddy is at this 0 just gets flipped to a 1, which means my buddy is this address. So I immediately know who my buddy is. I can check, hey, buddy, are you free? If my buddy is free, I coalesce with him. And then I now have a bigger block that is a free block of 256K. Then I can actually look at this bit. I can know that this one's buddy is the same as just flip that bit from a 1 to a 0. In this case, the buddy is not free because the buddy is starting at the beginning. It would be all 0s. So my buddy is not free, so I would stop after 1 coalescing. But I would do log n in the worst case. All right, other considerations. Allocation patterns, kind of discussed that, brought up. If you know allocation patterns, you might be able to do a better job. You might have different structures you could do. Lists are definitely one. People like that, but there's other structures. Generally, block lifetime's not random. They can ramp up, they can plateau. They can have peaks where there's a lot of short-lived objects. So people have studied this even in 1992, and they found that most of the allocations were only for things over half, up to 93%, were just for requests of the top two sizes. So if you optimize those cases, well, that's the most frequent case, you can do pretty good. And an allocator, you're going to try and attempt to exploit patterns, but you have to be general because some program might not exhibit the same patterns. But generally, when people allocate, generally the allocations might have similar lifetimes if they're allocated together. So you might want to allocate them somewhere close in memory together so that you can coalesce them together more easily. We saw linked lists. The list can be stored within the space or not. We might have poor cache locality, like with fat tables. Whenever we talked about file systems in 344, maybe in order to get better cache locality, maybe use some separate space to keep track of all the pointers all together so that traversing them is a lot faster. Again, that's up to you. We discussed that a bit later. And then, whatever, we're at time. I'll just end here. Happy Thanksgiving. So just remember, pulling for you.